Hi folks, this video is about transformations of exponential functions. So we've done lots of transformations before, so this might be mostly a review, but we're really going to focus on our exponential functions today. So over here on the left, you'll notice that I've shown just the standard function y equals f of x, and there are four different parameters that we can change, a, b, c, and d. So just as a reminder, a is a vertical expansion, and to be specific, by a factor of a. B is a horizontal compression by a factor of b. C is the horizontal shift, whether it be left or right. And D is the vertical shift that can be up or down. A, the vertical expansion, happens in front of the base. B, the horizontal compression, is in the exponent. The horizontal shift also happens to be in the exponent. And the vertical shift happens outside of the exponent. And one last quick little reminder that the order of our transformations matters. So first off, we're going to do the expansions and the compressions. Vertical or horizontal doesn't really matter. Then we'll do our reflections. And you could really flip the order of these ones. You do the reflections before you do the compressions and expansions if you want to. The order of these two isn't so important, but the shifts definitely must be last. So shifts go third on our list, and just my personal preference is compressions, expansions, and then reflections, and then our shifts. So we're going to start off just by stating how each of these exponential functions have been transformed from what I'll call our original function, f of x equals 2 to the power x. So the difference here is this 3 out in front. So that's our a value. So that's going to be a vertical expansion by a factor of 3. Over here, the difference from our parent function is this 2. So that is going to be a horizontal compression. Example number 3, this plus 1 is different, and that is going to be a horizontal shift of 1 unit to the left. Now example number 4 looks quite similar to example number 3, but this minus 1 is no longer in the exponent. It's the same size, if you will, as the base. So this is a vertical shift 1 down. For our next examples, we actually have two things happening. So we have this number that's out in front of the base. So this is going to be a vertical compression. And then we have this horizontal shift. So first off, we have a vertical compression. And then we have the horizontal shift. Our next example, we have this number multiplying our unknown in the exponent. And then we have this other number, which is what I'll call the same size as our base. So we have to do our compressions and expansions first. 0.5 is a horizontal expansion by a factor of 2. And then this plus 1 is a shift 1 unit up. And our last two, we have this negative that's out in front of everything, and then we're subtracting 1 in the exponent. So negatives are reflections. The negative out in front is a reflection over the x-axis. And the minus 1 is a shift 1 unit to the right. Our last one here, we have this number that's out in front, and we have this negative that's multiplied in the exponent. So it's a vertical expansion. and then we have a reflection in the y-axis. Now we're going to sketch each of those graphs that we just wrote down how they were changed. So there's two ways you can do it. You can start with our base or original graph, which is y equals 2 to the power x, which is given for us. And method one is to create a new table of values and then plot those points, which is absolutely fine. If you want to do the table of values, that's fine. I just think it might be a little bit easier if we move away from that and just apply the transformations to the curve that's already there. So I'll fill in the table of values as well, but I'll show you what that looks like on the graph. So here we have 3 multiplying by our previous y value. So 3 times 8 is 24, 3 times 4 is 12, 2 times 3 is 6, 1 times 3 is 3. And then we get some awesome fractions like 3 halves and 3 quarters and 3 eighths. So 3 was multiplying our original function here, which is y equals 2 to the power x, multiplied by 3, so each time we multiply by 3. In terms of how this affects the graph, it's a vertical expansion by a factor of 3. So we're multiplying all of the y values by 3. So 1 times 3 is 3. 2 times 3 is 6. 4 times 3, we're off the charts. 1 half times 3 is 3 halves, so that's 1 1/2. At an x value of -2, we were at 1 quarter, so 1 quarter times 3 is 3 quarters. So that's right here. And then we were at 1/8. 1/8 times 3 is 3/8. Then we're just going to play connect the dots as best we can, making sure there's arrows on both ends. And we also have to put in an asymptote. So trying to vertically expand the asymptote does nothing. So there we have our first one. Example number 2. So I'm going to do the graph first on this one. And we have a horizontal compression by a factor of 2. So if I start with the asymptote this time, that really doesn't affect anything. We still have the asymptote there because compressing it horizontally doesn't, it goes to infinity in both directions, so we're still good. And then the compression by a factor of 2. So the x values get cut in half. So 1 goes down to half, and 2 goes down to 1, and 3 goes down to 1 1/2. X value of 0 stays at 0. -1 goes to -1/2. -2 goes to -1. -3 goes to -1 1/2. And that's probably as many points as I want to sketch. So again, we're going to do as good a job as we can to get through all of these points in as smooth a curve as we can, making sure there are arrows on both ends. This is an example where I would probably just sketch the transformation as opposed to using the table of values, but we can certainly use the table of values if you want to. So let's just plug in here for x. So 2 times 3 is 6. 2 to the power of 6 is 64. 2 times 2 is 4. 2 to the power of 4 is 16. 2 times 1 is 2, so 2 to the power of 2 is 4. 2 times 0 is still 0. Anything to the power of 0 is 1. -1 times 2 is -2. 2 to the power of -2 is 1 quarter. Negative 2 times 2 is negative 4. 2 to the power negative 4 is 1 over 16. And then negative 3 times 2 is 6. Sorry, negative 6 to the power negative 6 is 1 over 64. So I think just moving these points left and right is easier than doing these calculations. That's just my preference. Next example, how does this affect the original graph, which shifts us 1 unit to the left? So if I start with my asymptote and I move it 1 to the left, it's still going to be the entire x-axis, so that stays the same. And then let's just move the points 1 unit to the left. So this guy here at 3 goes over to 2. This one at 2 goes over to 1. This one at 1 goes over to 0. X value of 0 goes to negative 1. Negative 1 goes to negative 2. Negative 2 goes to negative 3. And negative 3 goes to negative 4. I'm not going to bother plotting that one. And we draw our smooth curve. Smooth as we can make it. Arrows on both ends. And again, you can fill in the table of values if you like to. So 3 plus 1 is 4. 2 to the power 4 is 16. 2 plus 1 is 3. 2 to the power 3 is 8. 1 plus 1 is 2. 2 squared is 4. What you might notice is that the number here is just moving down 1 in the column. Let's just make sure that works one more time. So it's putting 0. 0 plus 1 is 1. 2 to the power 1 is 2. So every time the number gets moved down 1. This example, this minus 1, means we're moving the entire graph down 1 unit. That includes the asymptote. So the asymptote, which was at 0, now gets bumped down to negative 1. So all of our coordinates just get bumped down 1. So 8 goes down to 7. And then the next nice one is 4 goes down to 3. 2 goes down to 1. 1 goes down to 0. And then this was 1/2, goes down 1 to 1/2. This was 1/4, goes down to negative 3/4. If you want to get really precise, that's 1/8. If you subtract 1, that's negative 7/8. I'm not going to plot that one because we'll get the gist of the shape just through these points. And as best you can, go through all these points with a smooth curve and put arrows on both ends. Because the y value is decreasing by 1, we're moving it down. Every time we're just decreasing this number by 1. Now we're starting to get into the examples where we have multiple transformations, and now the order that we do things in could make a difference. So we have this 0.5, which is a vertical compression by a factor of 2, and then we're shifting 1 unit to the left. So I'll switch it up to do the points in red first. So this is 0.5 is a vertical compression. So 8 gets bumped down to 4. Our next nice point is at 4 cut in half is now 2. 2 cut in half is 1. 1 is half. Half is 1/4. You'd say 1/4 is 1/8, but I'm not going to bother plotting that one. Well, don't think it'll make a difference, but put that there. And then the next thing we want to do is we want to move everything 1 unit to the left. So I'm not even going to bother sketching the curve. I'm just going to move these points over. So 1 unit to the left. So this was a negative 2, goes to negative 3. This was a negative 1, goes to negative 2. This was at 0, goes to -1. This was at 1, goes to 0. 2 to 1, 3 to 4. And connect the dots with a nice smooth curve. You may notice that this is going to be the exact same as the original. So funny coincidence there. And we can't forget to plot the asymptote. So vertically compressing at the asymptote does nothing because it's on the x-axis, and then shifting it left or right does nothing for it. The asymptote stays in that same spot. Now we'll fill in the table of values. So vertically compressed by a factor of 2, so we're cutting the y values in half of the previous one. So 8 divided by 2 is 4, 2, 1, 1/2, 1/4, 1/8, 1/16. Then we end up shifting everything to the right. I think it's probably easiest, if you want to do table of values in this case, is just to basically plug the x values in and evaluate all the way through. So 3 plus 1 is 4. 2 to the power of 4 is 16. Cut that in half, we get 8. Okay. 2 plus 1 is 3. 2 to the power of 3 is 8. 8 cut in half is 4. And you'll notice that the original in this one scenario, we get the same values over here. So you can do all these calculations if you so desire, but the pattern will hold up, and it shows because our curve ends up on the same line. Again, here's one where we have a couple of things going on. First thing we want to do is this horizontal expansion by a factor of 2. So I will move all these by expanding them by a factor of 2. So x value is 0, 0 times 2 is still 0, so this point stays the same. Here we have an x value of 1, double that to get to 2. Here we have an x value of 2, we double that to get to 4. And then all of these points are going to be off of our graph, so I'm not going to bother plotting those. To expand this one horizontally, x value is -1, now it's -2. -2 gets bumped out to -4. And then everything else just is too wide for us. And we could plot the asymptote, but it's going to be the same asymptote that is already there. What happens next is we add 1. So this is a vertical shift of 1. We're moving 1 unit up. So we're going to take all these points I just found, move them up 1. And we can't forget to move the asymptote. It was at y equals 0. Now it's going to be at y equals 1. Then I can plot or sketch the curve. Arrows on both ends, make sure I don't cross the asymptote. So our table of values, 3 times 0.5 gives us 1.5, and 2 to the power of 1.5, that's really tough to say, especially if we don't get a calculator, and for most of these sketching questions, you're not going to get a calculator. So I'd be fine if you use the table of values and leave this one blank, but it's actually going to end up looking like √8. I don't expect you to know what that is as decimal. You probably compare it to the perfect roots of perfect squares around it. So √9 is 3, and √4 is 2. So you know it's going to be between 2 and 3, closer to 3, but I don't need you to approximate that. 2 times 0.5 is 1, so 2 to the power 1 is 2. And then we get another 1 here, so 1 times half is half. So 2 to the power half, that's tough to get an exact value for, so that just simplifies to √2. And Then we get 1 over root 2, 1 over 2, and 1 over root 8. Again, this is my argument for why I would not use a table of values. Then we do the next piece where we bump everything up 1 unit. So root 8 plus 1 might look awkward, but it's root 8 plus 1. 2 plus 1 is 3. Root 2 plus 1 is root 2 plus 1. 1 plus 1 is 2. And then we get these other ones, which are probably less fun at this point in time. 1 plus 1 half is 1 1/2. Well, I don't like writing it that way. Let's call it 3 halves. This is 1 plus 1. On to the last couple. Here we have a vertical expansion by a factor of 3, and then we have a reflection in the y-axis. So the order we're going to do things in is a vertical expansion by a factor of 3. So I'll take all of these points and I'll multiply the y values by 3. So 1 times 3 is 3. 2 times 3 is 6. 4 times 3 is off the grid. 1/2 times 3 is 3 halves. 1/4 times 3 is 3/4. 1/8 times 3 is 3/8. The next thing we're going to do is reflect everything over the y-axis. So that's the left-right flip. So here our x value is 1. That moves over to -1. The point with an x value of 0 stays at 0. X value of -1 moves to x value of +1. X value of -2 moves to an x value of +2. And x value of -3 is x value of +3 now. And we connect these points with as smooth a curve as we can make. Make sure there's arrows on both ends. And we can't forget the asymptote. Vertically expanding the asymptote, because it's on the y-axis, on the x-axis, that really does nothing. And then reflecting it also does nothing. So it stays in the same spot. Table of values for this one. This is the same as actually our first graph. So 3 times 2 to the power x. Multiplying all these by 3, so we get 24, 12, 6, 3, 3 halves, 3/4, 3/8. Then we end up reflecting everything in the y-axis. So again, using the table of values, I would just plug this in up here. So 2 to the power -3 is 1 over 8. And then we have to multiply that by 3, so we get 3 over 8. 2 to the power -2 is 1 over 4 times 3 is 3 over 4. Our next one is 3 over 2, 3, 6, 12, and 24. Last but not least, again, we have multiple transformations. We have this reflection in the x-axis, then we're shifting horizontally. So we'll start with the reflection. So all of the y values now become negative. So this is 5, 6, 7, 8. So we go down to -8 down here. Here's 4, goes down to -4. That looks like a 2, so it goes to -2. 1 goes to -1. 1/2, -1/2. 1/4, -1/4, and that's about as precise as I care to try to get. And the horizontal asymptote doesn't change because it is on the x-axis. Next up, we're going to shift everything 1 unit to the right. So that gets bumped over here. This one moves over there, and so on and so forth. And we can try to sketch a nice smooth curve through these. And don't forget the asymptote. So our table of values, we're reflecting in the x-axis. So we get all of these values turn negative. And then I would plug in this 3 here. So 3 minus 1 is 2. 2 squared is 4. So negative 4. 2 minus 1 is 1. 2 to the power 1 is 2. So negative 2. Pattern that I'm noticing is the one below it is shifting up 1. Let's see if it works again. 1 minus 1 is 0. 2 to the power 0 is 1. Negative 1. You look at that. It looks like it's going to hold all the way through. And our last one's negative 1 over 16. There you go.